Hello, in this video I'm going to look at other methods of integration by tables or formulas. So what that kind of means is that, for instance, let's say that you have an integral that you're working on. So what if that integral was the following? What if it was the integral of, let's say, like x squared e to the x dx? And you're like, okay, well, how do I solve this, right? And you're like, oh, okay, well, that looks like a product of two functions, meaning that I have an f and a g, and I need to name one a u, and I need to name one a dv, and then, okay, yeah, somehow it's just supposed to equal to an easier integral, right? But in any case, you know that, yeah, if you can recall the formula that is for, yeah, integration by parts in this case, which is uv minus the integral of v du, and of course that's equal to the integral of u dv, then in any case, yeah, we can probably solve this using our favorite method of integration by parts, for instance, which, like, let's say, for example, that we were to go ahead and do this by the use of tabular method. Then, of course, yeah, we know that we can choose our u to be the x squared. So then we have x squared, then we have 2x, then we have 2, and then we have 0, where we differentiate on the left-hand side and we integrate on the right-hand side. So we have e to the x, e to the x, e to the x, e to the x, and then each sign basically alternates because you have a plus sign, a negative, a plus sign, a negative. And then when we put it all together, we're like, okay, well, we have x squared times e to the x minus 2 times e to the x minus 2x, and then we have plus 2 times e to the x, and then finally we have the plus c. So then, okay, then we're like, well, I can write down my solution as finally x squared minus 2x plus 2 times e to the x plus c, and okay, sounds simple enough, or looks simple enough, and I think I got it. But then, what if we were to keep repeating this whole process and we start to notice a pattern? So in any case, that means that using, whether we're deriving a formula for something of the form, let's say like x to the power n times e to the x dx, we could probably derive a formula for this, for example, doing integration by parts. But does that really simplify the process necessarily? Not so much, because we're still like, okay, well, I need to get a formula, right? So we have x to the n, and then we have n times x to the n minus 1, and then we have e to the x, and then we have e to the x, and then of course we're like, okay, well, the signs, they alternate, so then in any case we have that this would be the integral of, well, not the integral, right? It would be x to the n e to the x minus, so in any case it would be minus n times the integral of x to the n minus 1 times e to the x dx. So we have a nice formula in this case for a exponential function of power n, or yeah, x to the n times e to the x, right? So in any case, like, look at how if we were to apply this formula for the x squared e to the x using the one that I just derived, using integration by parts though still, so x squared e to the x dx equals to x squared e to the x minus, well, the power is 2, so we have 2 times the integral of x to the 1, because 2 minus 1 is 1, times e to the x. But notice that you still have another integral by parts. So in that case, that means that we have to do it again. So we have x squared e to the x, and then from there we have minus 2 times the, okay, so we have to use the integration by parts again, or the formula, which is in this case x e to the x, and then we have minus, Well, that would be the integral of, well, in this case we have e to the x, and then of course we just have to finish the integral by saying that we just integrate e to the x, which that gives us basically x squared minus 2x plus 2, and then we integrate the last term, as we mentioned, as e to the x plus c. So we end up with the same exact thing, but in this case I used a formula. But in this sense I had to derive the formula in order to solve it still. So I still did almost as much work. Whereas like if I had this formula available, then I can probably just apply it as needed for any power n. Okay, so that's kind of the basis of this topic of integration by tables or formulas. So yeah, what if I was to go ahead and create a formula sheet that had, the integral of x to the n times e to the x dx, and then I know that yes, it is x to the n e to the x minus the n times the integral of x to the n minus 1 times e to the x, and then I have dx. So okay, so that's my first formula that I can probably apply if ever I had a integral of this form. Okay, but in any case, what if, for example, that we had a value right in front of this x? That changes everything, because like, for example, like what if I had the integral of x squared, and then I have e to the x over 4 dx? Well, accordingly, I wouldn't be able to use the formula technically, because I would have to do a substitution. I would have to say that u is equal to x over 4, which means that 4u equals to x, which means that 4 du equals to dx. Okay, but if that's the case, I also have that x squared is equal to 16u. So in that case, that means that this integral now becomes the integral of, that should be a squared, by the way. Okay, so I already made an error. So 16 times u squared, and then we have, that's going to be multiplied by e to the u, and then that's going to be multiplied by the dx, which in this case is already 4. So we have 4 du, of which now we have 64 times the integral of u squared times the e to the u du. But now, of course, this is just a repeat of the previous problem in a way. But the only difference is that once I find my antiderivative, I need to substitute back basically the u as x over 4. Okay, well that sounds like a lot of work in either case. But luckily there is a formula that we can use. So there is a formula that involves a variable x to the power n times e to the coefficient x. And what I'll do is I'll actually write it down. Now it's actually in your D2L course as a PDF file, of which there are 108 of them. Believe it or not, there are 108 integrals that are actually there in different formats. So you have e to the ax dx, and we refer this integral as number 102. Okay, so number 102 is going to be this integral, of which apparently it's going to be 1 over a times x to the n times e to the ax minus n over a, and then finally you have that you're just integrating x to the power n minus 1 times e to the ax, and then of course you have that that's going to be dx. such that your a is not equal to 0, because then otherwise this would be undefined. So the question now becomes, how do we solve the exact same integral by using this formula that we have right here? So notice that in either case we have that n is equal to 2, but what is a equal to? Okay, well, a is equal to actually 1/4. So that means that our integral is going to be equal to 1 over 1/4. Then we have x to the second power, and then we have e to the x over 4, and then we have minus, okay, so we have the power 2, so that's going to be 2 divided by 1/4, and then that's going to be the integral of, so n is equal to 2, so that's going to be x actually, so it's going to be x, and then we have e to the ax, so that's going to be x over 4, and that's going to be dx. But notice that we can actually rewrite this one time where we have 4x squared e to the x over 4, and then we have minus 8, but now it looks that we have to reapply the entire formula all over again. So we have, okay, so we have that now we're going to use that n is equal to 1 and a is equal to the same value. So we have 1 over 1/4, and then we have x e to the x over 4 minus, okay, so this time you have that the n is equal to 1, so you have 1 over 1/4 as well. And then now you have that you're integrating basically the x to the 0, which in that case will just be 1, times e to the x over 4. Okay, but we have to basically close that essentially, and that's going to be dx, right? Okay, now not to get lost, we're going to go ahead and just say 4x squared e to the x over 4. And then notice that that becomes a 32x, so minus 32x, and that's going to be e to the x over 4. But notice that over here, that's going to also be 32 when you distribute the 8 across the subtraction. So you have that that's going to be 32. However, notice that basically you have to multiply by a 4th also. So it's actually going to be minus, or plus in this case, plus 128. And then notice that essentially it's going to be multiplied by e to the x over 4, and then you have plus c. So here is our integral of e to the x over 4 times x to the second power using the formula that we have right here referred to as number 102. Now we can actually rewrite this if we want to. We can actually rewrite this as the following. Note that, for example, you have that 4 is a common factor, and also e to the x over 4 is also a common factor, so that basically leaves you with x squared minus 8x, and then of course, let's see, if you take out a 4, that's going to be also 32, so that's going to be plus 32, and then this would be the answer. Of course, don't forget the plus c. And just like always, you know, like if you differentiate this, this actually gives you the exact same thing. Now, what if, for example, that we were to consider a different type of function? So if we were to consider a different type of function, so let's think about the following integral. So let's say that we have the following integral, 1 over x times the square root of x plus 1. And then we'll put dx, okay? Now this one is actually pretty special because notice that we could probably solve it immediately by the use of u substitution. But to do that, you would probably need to say that u is equal to the square root of x plus 1, and then you would say u squared is equal to x plus 1, and then from there you would probably then say that, okay, well, if I differentiate this, I will get 2u du is equal to dx, and then from there we see that u squared minus 1 is going to be equal to x. Notice that basically that would reduce the integral into the following. It would reduce it into 2u divided by u squared minus 1, and then you have the whole thing u, and then du. But then that becomes basically 2 divided by u squared minus 1. And of course we're still integrating that. But then it becomes a question as to, well, how do you even solve the integral of, say for example, 2 divided by u squared minus 1, in this case du. So the question can be answered by the use of partial fraction decomposition. But notice that I've already used one method in this case, which is u substitution. So there is actually another way that we can do this question. So this question has that the integral is of the following form. I refer this as to integral number 89. Integral number 89 says that you have an integral 1 over x times the square root of ax plus b, and that's going to be dx. This is equal to 1 divided by the square root of b, and then you have natural log of the absolute value of the square root of ax plus b, and this is going to be minus the square root of b divided by basically the conjugate. So you have ax plus b, and then you have plus the square root of b, and you just close it and you have plus c. Now the only condition upon this is that basically you have that a is not equal to 0 and that b would be positive. So in this case we have that, these are the conditions upon the constants, but note that basically this would be an integral that involves a form of ax plus b. Now for that matter, you could probably say that, okay, well maybe I can apply this to the negative case. It's going to be a little bit different for when the b is going to be still positive but with a minus sign. That's actually going to be a different format. So in either case, let me go ahead and just remove that just so that there's not any confusion as to does this apply to both when it's a minus b? And the answer is no, it has to be ax plus b in this case. So, and that'll be interesting if you can look at a integral where the sign is negative. So this is our integral that we got from a table, of which that we have that the integral of 1 divided by x, and then we have the square root of x plus 1, and then dx. It says that basically b is equal to 1, and a is also equal to 1. So here we have basically the natural log of the absolute value. So we have the absolute value of the square root of x plus 1 minus 1 divided by the square root of x plus 1 plus 1. And then from there, let's see, that's going to be plus c, right? Okay, now technically we can rationalize this in either case by multiplying by the conjugate. But you'll notice that when you when you multiply it by the conjugate in the denominator, basically what's going to happen is that this right here is going to get squared. Okay, so this gets squared because it's going to be multiplied by the root x plus 1 minus 1, which, that's going to be its own, rewritten expression and such. So in actuality, this is the solution. So we have that this is apparently the solution because there was nothing to account for in terms of the chain rule in either case. So we can actually just leave it like this, but it would be interesting if we can basically show that when we take the this as your u, this whole thing as your u, and you apply the partial fraction decomposition, that you actually get the exact same thing, of which you will get the exact same thing if you apply the partial fraction decomposition. You will get the exact same answer in actuality. Okay, so this is actually kind of a fun exercise, like whether you're going to use partial fraction decomposition or if you are going to use the formulas. Now, let's look at some partial fraction decomposition. So for example, let's say that we have an integral of 1 over x squared minus 4, and this is going to be dx. Now, basically, I know that I can essentially just rewrite this as a over x minus 2 plus b over x plus 2, and then from there, I just need to figure out what is the a, what is the b, such that it reduces down to this. But, that can be a task in itself, of which that we end up with, like 1 times a x plus 2 plus b times x minus 2, and then, we're like, okay, well, a plus b equals to 0, and then we're going to say that, for instance, that 2a minus 2b is equal to basically 1. And then from there, we'll just try to figure out, how to solve for a and b respectively. And, that's not too difficult. We can actually figure that out. As to, like, what is going to be the value a and b respectively. Okay, but accordingly, we don't need that because we have another integral. That we can use that I believe we just call it integral 74. So integral 74 says that when you integrate a difference of squares, like 1 over x squared minus a squared dx, that it's going to be equal to 1 over 2a. Okay, so we have 1 over 2a, and then we have the natural log of the absolute value of x minus a over the the x plus a. And then from there, that's going to be plus c. Now, notice that in this case, that the previous problem actually looks very similar because you had a 2 at the top, okay? So we can go ahead and apply the table value, or the formula. So accordingly, we have that the integral of 1 over x squared minus 4 dx is equal to Okay, so we don't even need to use the partial fraction decomposition because we know that a is equal to 2. So in that case, we have 1/4, and then we have natural log of the absolute value of x minus 2 divided by x plus 2, and then we have plus c. And then that would be it, actually. We have the formula allows us to solve for the integral right away. So in this case, this is very convenient. Now, we can actually look at another integral, of which in this case, what if we had an integral that was of the form from a to b, so let's say like from 0 to 4, of 4 divided by x squared plus 16, and then we have dx. Well, okay, this integral actually resembles the integral of 1 over x squared plus a squared dx, and this is equal to 1 over a arctangent of x over a, and then it's plus c. Now, in actuality, this integral in the tables is referred to as number 13. So number 13 says that this is the indefinite integral, but here we have the definite integral. So that's just one adjustment that you would need to make in actuality when you use the table. So here we'll just go ahead and say, well, by integral number 13, we know that a constant is being multiplied, so we have a 4, and then we have that that's just going to be times, well, it's going to be times 1/4, that's for sure. You have 1/4. Then you have tangent inverse of, okay, this case you have that the x is still there, so there's no need to account for chain rule technically. So you have x over 4. And then now you just evaluate this from 0 to 4. Now, notice that basically this cancels out, and it leaves you with tangent inverse of x over 4. And then that's going to be from 0 to 4, but that gives you tangent inverse of 1. But tangent inverse of 1 is basically pi over 4. So essentially we found that the answer, the solution, is actually pi over 4. So there's our area, or solution to the definite integral without using integration by parts, or without using a u substitution, or without even using a trigonometric substitution. Now, sometimes you might run into integrals of which that may be a little bit complex, for example. So let's say that you had an integral. Let's say the following integral. You have x squared divided by the x squared plus a squared squared, and then this is dx. Now, using basically partial fraction decomposition may not be a good idea, but this can actually be solved by either trigonometric substitution or even integration by parts. Now, in actuality, there is a formula that can be derived. For example, once you actually derive the formula, you will get the following: 1 over 2a arctangent of x over a, and then you have minus 1/2, and then you have x over x squared plus a squared, and then it's going to be plus c. So this is actually a nice little formula that I was actually able to derive by the use of integration by parts, but I also verified my answer by using trigonometric substitution. Once I got that, then I was kind of convinced that I could probably just save this in case the integral ever comes up again, and then I don't have to do it again from scratch. Okay, so we can actually apply this, for example, to the following integral. What if we were integrating x squared divided by x squared plus 1 squared dx. Well, accordingly, a is equal to 1, so automatically I have 1/2 tangent inverse of x plus, actually it's not plus, but minus 1/2, and then you have x divided by x squared plus, that should just be a 1, and then we have plus c. So this is our answer actually. Now imagine if you were working on this and you say, for example, needed to get the solution really quick, then you would actually find that this is a lot faster because we have this nice little formula, which means that if I had a definite integral, then in that case I can just substitute into the formula, and then now I have my answer. Because for example, you could have an integral that says that you have the integral of 2 pi from 0 to 1 of x squared over x squared plus 1 squared dx, and then now you're just expected to basically find what the area or volume would have to be in this case. For this particular question, this is actually the volume for a solid that's rotated about the y-axis by the use of shell method, which in this case, now that you have a formula for this particular integral, that means that basically the rest is just plug into the formula, and then we get the volume of the solid that's rotated with respect to the y-axis. Isn't that cool that we can actually avoid using integration by parts and other techniques that we learned?